Okay, good morning. This is Professor David Okay, my topic for this morning will be a continuation of my AC machines long video format discussion. And I am now, and we are now on lesson number 28. Okay, let's proceed. The topic for this morning will be AC machines, lesson number 28. The title of the topic is Parallel Operation of Transformers. This is a very interesting topic on the study of AC machines because in real life, actually to get our power from the uh, utility companies used to operate transformers in parallel, and this will be the one we will be discussing this morning. Okay, let's try to bring out the figure on how to connect two transformers in parallel. Okay, these two lines here are the so-called primary line. This comes from the power plant. It could be a nuclear power plant, diesel electric plant, solar energy plant, hydroelectric plant. So this is the primary thing. The first transformer is actually connected to the primary line. This should be line number 1 for transformer number 1, and this is line number 2 still for transformer number 1, line number 1 for transformer number 2, and this is line number 2 for transformer number 2. Okay, this is the primary side of transformer number 1, primary side of transformer number 2, secondary side of transformer number 1, secondary side of transformer number 2, and this is the load. Okay, the load is connected since the connection is parallel. Okay, we'll make the connection immediately for transformer number 1. It goes to one terminal immediately, this one here, and the other line number 2 of the secondary portion goes to the other terminal of the load. And for it to be said that they are connected in parallel with transformer number 2, okay, this portion here should also be connected to the other terminal, right? And this portion here should be connected to this. So they are in parallel. So actually, when we try to close the two switches over here, okay, where the switches are closed already, the two transformer secondary is actually feeding the common load. These two lines here are connected with the same terminal on the load, and these two lines on the lower side, hold on, yeah, it's correct, upper side. Oh, they should go to the other side because this is the upper portion, right? This is top portion goes with this, so this one should go here. Okay, we cut this one, and this one should go here. Okay, upper, they should be connected to the same point, and lower should be connected to the same point. So we could say that they are connected in parallel. Okay. The specification of the voltages are these: BP1, BS1, BP2, BS2. Subscript 1 refers to transformer number 1. Subscript 2 refers to transformer number 2. So the current delivered by transformer number 1 is IS1, and the current delivered by transformer number 2 is IS2. Okay? So if we try to take the simplified equivalent diagram of this one, we apply our knowledge on the study of AC circuit. Transformer circuit are actually AC circuit. And if we try to simplify this one, it is this. This voltage here is the voltage across this. And this voltage here is this voltage here. So these are the secondary voltage of transformer number 1, secondary voltage of transformer number 2, okay? They are connected to the same point on the terminals of the load. It is this. Right? For transformer number 1, there is an effect of the copper loss, right? That's why we specify impedance on the secondary side for transformer number 1. Okay, this is the equivalent impedance of on the secondary side of transformer number 2. Okay, there is a copper loss. And this should be the load. The current delivered by transformer number 1 is this one. And the current delivered by transformer number 2 is this one. The sum of IS1 and IS2 is actually the load current. Okay. Okay, let's try to bring out the requirements for ideal operation. This is very important actually. Number 1. The same voltage ratings for both the primary and secondary. Okay, that's very ideal, right? Meaning to say, the primary voltage of the first transformer should be equal to the primary voltage of the second transformer. Okay? And so with the secondary. Okay? That's the meaning of this one. What's the effect of this requirements number 1 if this requirement is not met? If requirement number 1 is not met, it says here, there will be a big circulating current. Of course, supposed to be there is a big circulating current. Why? Assuming 2300. And this voltage here is 3000. Okay? So if you apply 2300 here, and you apply to 3000 over here, this is from the secondary transformer number 1, assuming they are not equal. And this is the secondary voltage of transformer number 2. So if this is 2300 and this is 3000, okay? This 3000 is greater than this, right? So actually, the current that will be delivered by this terminal here will push this one, will push this current here. Okay, it will push because this is bigger than this one. So what will happen? There will be a circulating current. Okay, that's the meaning of that one. So it's a must that if this is 2300, the other one should also be 2300. Why? If this is 2300, it seems it's just like a water flow, you know. 5 gallons per minute, this is 5 gallons per minute, okay? It will be balanced. But if this is 10 gallons and this is 5 gallons, these 5 gallons will be overpowered by this 10 gallons. So actually, the flow will not just simply flow to the load, okay? It might go back to the other circuit. That's the term, there will be a big circulating current. But if they are equal, okay, when they deliver current, okay, for sure the current will go all through the load. Okay? Because upon reaching this terminal here, IS1 will just go down like that, and IS2 will just go down like that. So they will add up. Okay? The current will be twice. You know, that's why the operation is parallel, is to aid each other in the giving of current to the load. Okay, that's requirement number 1. What must be requirement number 2? They must be of the same polarity. Same polarity meaning if this is the voltage around the secondary of the first transformer, the voltage of the second one should also be the same. I mean, how it come out as an alternating current, they should be the same. Okay, that's the meaning of same polarity, meaning they are in phase. Because if the other one is ahead and the other one lags behind, okay, there will be a big circulating current. Okay, there will be a big circulating current, and according to the consequences, which might burn the windings. So the polarity requirement is actually very important. For number 1, there will just be simply a big circulating current, but for consequences number 2, if it is not met, there will be a big circulating current which might burn the windings. For sure, there will be a big circulating current. That's the meaning of they must be of the same polarity. Number 3 and number 4, I think we should derive this one the next time around. It is just the ratio of the impedances should be equal to the ratio of the apparent powers. But if this is subscript 2, the numerator on the right hand side will also be subscript 2. Okay, so CE1 over CE2 should be equal to KBE2 over KBE1. That is impedance ratio over apparent power ratio. And for number 4, RE1 over XE1 should be equal to RE2 over XE2. What comes out, these should be of the same power factor. Because the ratio of resistance over impedance is actually power factor. The cosine of theta of the power triangle, this is theta. Okay, this is R, this is Z. So the ratio of R over Z for both transformer number 1 and number 2 should be the same. And according to the consequences, okay, if requirement number 3 and number 4 are not met, according to the consequences, the transformers will not deliver power in proportion to their capacities. Okay? The proportionality of the current that will be delivered to the load will not be in proportion to their capacities if these 2 equations here are not met. That's why the impedances of transformers is actually determined, right? It's from the short circuit and open circuit test we could determine those values. So if you know those values, we will be having, we know the ratio of CE1 over CE2 because we know it, okay? If we don't know it, we don't have a relationship for the impedances with respect to the apparent power. And according to consequences number 3 and number 4, if these 2 equations are not met, okay, the 2 transformers will not deliver power in proportion to their capacity. Okay? So meaning to say, the characters or the resistance and reactance of the 2 transformers should be the same. If they are not the same, they will not deliver power in proportion to their capacities. That's the meaning of that. Okay, that's it, guys. That's the way how to connect 2 transformers in parallel and how they will deliver load to the how they will deliver capacities in proportion to their impedances. Okay. So the next time around, we will try to derive this one, and we will try to compute the circulating current, just in case the 4 requirements are not met. Because for sure, there will be consequences if these 4 here are not met, and these are being specified by this one. So design engineers is actually what they call this, would like to know how much will be the circulating current just in case the four conditions are not met. Because the worst case scenario is that if there is a circulating current, how much will be the current? Right? Supposing you connect to transformers which have different voltage capacities, the polarities are not the same, and the ratio of the impedances with respect to the power are not the same. For sure, there will be a circulating current. So, design engineers are actually interested in the value of the circulating current. So, the next time around, on our next topic, we will try to derive the formula and how to compute for the circulating current. Okay, good morning from Los Angeles. This is Professor DavidJDelosReyes. This is a discussion on the parallel operation of transformers. Good morning.